Hey, here's a good practice problem on air resistance. So in this problem, we're given a mass of m that's initially traveling at time t equals 0 to the right with a speed of v naught and has a position of x equals 0 time t equals 0, and it's subjected to a velocity dependent force that points to the left. So the first question here is, what's the initial acceleration? Okay. So let's make a free body diagram. The ground pushes up on the block. We call that normal force. The block weighs something. We can calculate that as mg. And then pointing back to the left is a force with a magnitude of kV. Normal force and mg cancel each other out. So the net force is just negative kV. That means ma equals negative kV. So A equals negative kV over m. And there we go. Okay, part B, we need to derive an equation for velocity as a function of time. Well, we can do that starting with our result from the previous step. So we can write it as dv dt is equal to negative kv over m. And if we cross multiply, then we get dv over v is equal to negative k over m dt. And we can integrate both sides of the equation. So if we do that, we need to be sure of our limits of integration, match them up. At time t equals 0, the velocity is v naught, and at some later time t, the velocity is some other value v. So the left side of this equation, that integral comes out to the natural log of v divided by v naught, and the right side's really easy. We just get negative k over m t. Whatever we do to one side of the equation, we can do to the other, so we can take e and raise it to the expressions on both sides of the equation. And so we get v over v naught is equal to e to the negative k over mt. So our final result is that velocity is equal to initial velocity times e to the negative k over mt, which basically says the velocity starts out at some initial value and then exponentially decays. If we have to graph that, maybe we make a little data table and we make columns for time and velocity. At time t equals 0, when we evaluate this part of the expression, we just have e to the 0, which is 1. So at time t equals 0, yeah, exactly, the velocity will be v naught. Let's fast forward. At some very large value of time, now this expression is e to the negative infinity, or we can think of that as 1 over e to some very large value, which approaches 0. So right, the velocity starts out at v naught and then approaches a value of 0, but only after a ridiculously long amount of time. So when we graph that, we should see this exponential decay. So the velocity starts out at v naught and then it approaches 0 asymptotically. It exponentially decays towards 0. So here's our graph. Just looks like that. Easy enough. Next question. Derive an expression for distance as a function of time, and also sketch what that equation looks like when we graph it. All right, so we're going to take our previous result and use that as our starting point for part C. So v is equal to v naught e to the negative k over mt. That means dx dt is equal to v naught e to the negative k over m times t. By cross multiplying, dx is v naught e to the negative k over mt dt. And again, we can integrate both sides of the equation. Well, what do we get when we integrate dx? We get x. So we can get position as a function of time. Now let's put in our limits. At time t equals 0, the position is 0. And at some later time t, we have some final position x. Okay, So, right, yeah, the left side of the equation evaluates at x, and the right side comes out to v naught times negative m over k e to the negative k over mt. Remember, we're evaluating that from 0 to t. So we get x equals negative m v naught over k multiplied by e to the negative k over mt minus e to the 0. And that's the same thing as minus 1. Now, if we want to get rid of this negative sign, we can distribute it, right? We can turn this into a positive if we make this negative and this positive. Okay, so our final result then, x equals mv naught over k times 1 minus e to the negative k over mt. So what's that look like if we graph it? Let's see. T and x at time t equals 0, then we have 1 minus e to the 0, which is 1 minus 1, which is 0. Yeah, and that's exactly what we should get, right? The problem tells us at time t equals 0, it's at an initial position of x equals 0. No surprise. Okay, fast forward. After a very large amount of time, we have 1 minus e to the negative very large number, which is the same thing as 1 minus 1 over e to the very large number, which is like 1 minus 0, essentially. And so we get a final position of mv naught over k. But it approaches that asymptotically, right? So that's the graph of position as a function of time. So in fact, we've answered part D. Determine the distance the object travels from time t equals 0 to time t equals infinity. The answer is m v naught over k. Now wait a minute. Is that really going to work out? Would that give us units of meters? So do we know the units for the drag coefficient? Sometimes we call drag coefficient B. In this problem, we're calling it K. In either case, we know this much, that we get force when we multiply K times V. Okay, so that means K should have units of force units divided by velocity units, or in other words, kilogram meters per second squared divided by meters per second. So meters cancel out, and we have the same thing as kilograms times seconds over seconds squared. So we get kilograms per second. Now, I don't like those units very much because that sounds like a flow rate to me, right? Kilograms per second, that would almost be like if you had a really large version of like a hourglass, you know? Something that lets sand fall through a narrow opening to record time. So if you had a really big version of this, then you have a certain rate of mass falling into the lower portion of this hourglass, right? That's what I think of when I hear units of kilograms per second. So that's certainly not what drag coefficient is about. So to avoid that confusion, I find it better to say the units for drag coefficient K or B, I just say it's kilograms seconds to the negative 1. Okay. In any case, back to this, what units would we have here then? This would be kilograms times meters per second, all divided by kilograms seconds to the negative 1. Okay, so this is kilogram meter seconds to the negative 1 over kilogram seconds to the negative 1. Cancel, cancel, cancel. Oh yeah, meters. Yeah, exactly. And we were trying to find a distance. So looks like everything's working out in this problem.